All right, let's find that equation. So this is we're looking at the peak black body radiation. So let's find that. That equation is, oh, I see it. It's in subtopic 8.2. Subtopic 8.2, thermal energy transfer. Okay. So calculate the peak body radiation by the planet and the star. Well, this is the temperature of the star, right? And then the temperature of the planet is something like 302.689 kelvins, right? And there's the star's planet, right? Star is that, right? Okay, and then you're just going to use the Wien displacement law. So this is in 8.2 on page 8 of the data packet, right? And that is this guy. Equals 2.90 times 10 to the minus third. And that is, by the way, meters Kelvin divided by temperature, right? And then they do something weird, like they put the word meters and kelvins and all that stuff. But, you don't need to, right? So just plug it in there. Keep in mind that micrometers equals 10 to the minus sixth, okay? Nanometers is 10 to the minus ninth. Those are all in your data packet. So they're going to use those without explanation, without hesitation, okay? So this literally is 4.64 times 10 to the minus seventh, or 464 times 10 to the minus ninth, okay? Okay, this guy's going to be 9.58 times 10 to the minus sixth when you figure it out, okay? And then with reference to the wavelengths of the incident and radiated energy, explain how the surface of the planet would be warmer than the value you calculated in C, right? Remember that you've got this atmosphere, right? Let's if we have a fried egg, right? Okay. Remember that visible light can go right through this atmosphere, right? Short wavelength can pass right on through. Now there's some reflection, that's the albedo, right, of the atmosphere. But short wavelength light can just sail right through. It's transparent to short wavelength, right? And that's because, of course, this we can figure it out, right? But the radiation coming from the sun is very short wavelength, right? This is a very blue star, by the way. Okay, this would be a bluer world than ours, right? So that stuff goes sailing right through. But when the planet starts to radiate energy back into space, it's radiating at a large wavelength. This, by the way, is the infrared, right? This is IR spectrum, right? Okay. Oh, yeah, you're supposed to say which part of the electron. So this is visible light, right? This is infrared, right? Okay, the IR light that comes out like that, the greenhouse gases are resonant at those frequencies, right? And so the atmosphere will absorb the energy, the outgoing radiation. It slows this down, right? Okay, so it blocks some of this, transparent to the short wavelength, not as transparent to infrared, okay? And so the atmosphere absorbs the radiation, then it re-radiates it back to the Earth, keeping it warmer. Now, by the way, we have to have some greenhouse effect, but too much can be bad, okay? So without the greenhouse effect, we'd just be frozen. But with the greenhouse effect, we're just right. With too much greenhouse effect, we don't really know.